Hello, this is Brian Washburn. I'd like to give an introduction to the two-body central force problem. So consider this. Say I have a Cartesian coordinate system, and I have two masses, mass 1 and mass 2. And associated with that mass, I have a position vector. So R1 is a position vector from the origin to mass 1, and R2 is a position vector from the origin to mass 2. And so what I want to do is write down the equations of motion that describe this system, and there's only one force acting on the system, and that is a force between the two, and that force is a central force. And so what's a central force? A central force is such that the force, let's go back, the force between the two, okay, first of all, it only depends, the magnitude of the force depends on the relative position between the two, and it's in that direction r hat. So what is r? R is a relative vector between the two, so I'm going to define r as r1 minus r2. And then the r hat direction is basically in the direction of r. Okay. So in my little picture, if I subtract r1 from r2, that is a vector that goes from m1 to m2, so that is r. And then the r hat direction would point along that direction, so it would be a little vector, a unit vector like that right there. So then, so that's the central force, and that's the only force that's acting on the system. Now, central force is an internal force. So since it is an internal force, there's no net external force acting on the system. So that would mean that the linear momentum associated with the center mass is going to remain constant, and that's a big important thing. So how we're going to solve for the equations of motion, and what we're going to do is let's write down the Lagrangian for this particular system. So if I wrote it in terms of the R1 and R2, what I would have is, let's write down the Lagrangian. Lagrangian is going to be equal to, well, 1/2 m1 r1 dot squared plus 1/2 m2 r2 dot squared minus the potential energy, which depends on the central potential, which is R1 and R2 in general. Okay. However, that's a two-body problem because I have R1 and R2. And so that's a hard problem to solve in general. What I want to do is recognize that, okay, we think about what symmetries for the system. Time is homogeneous, so I expect the energy to be conserved. Space is also isotropic, so I expect the angular momentum to be conserved as well. And so when I have something like that, a better way of solving this problem, instead of solving the equations for R1 and R2, let's do it in a center of mass frame. And I know the center of mass is going to move with constant velocity because there's no net external force acting on the system. So I want to rewrite my Lagrangian not in terms of R1 and R2, but in terms of capital R. And what is capital R? Capital R is the center of mass. Okay, this is capital R here. And then also the relative distance, which is little r. And so I want to basically write my Lagrangian not in terms of R1 and R2, but in terms of R and capital R. And you can see it from the picture. So, R1 again is the position vector from the origin to mass 1. R2 is the position from there to there. I can define the center of mass. Okay, the center of mass, and we've done this before, it's a position vector that goes from the origin to where the center of mass is system. That's going along the line connecting the two masses. So this is the center mass, say, for here. And then R, which is the relative position, which is what we defined before. So what I want to do is rewrite my Lagrangian in terms of capital R and little r. The other thing that allows me to do this is since the force is central. Okay, again, this is my definition of a central force here. I would expect the form of my potential energy. Well, here I wrote it as a very generic. This is very generic, but really U is going to really be a function of the difference between the two. Okay, or more specifically, the magnitude of the difference. So U is really going to be a function of R by itself. And that's really useful because then it will not be a function of capital R. And so we'll see what comes from that. Okay, so now what I want to do is rewrite the Lagrangian I have there in terms of, instead of R1, R2, little r and big R. So let's do that next. Okay, so here is my Lagrangian, okay, in terms of little r1 or little r1 and r2. And I want to rewrite this Lagrangian in terms of small r and big R. And how do I do that? Well, I can use the definitions of the relative distance between the two and the center of mass, and I can easily show that R1 is equal to capital R, minus M2 big M, and then big M is the total mass, divided by times the relative position between the two. So that's R1. And then remember what I'm going to do in the end is I want to calculate R1 dot. So I can calculate R1 dot is going to be equal to R dot minus M2 M R dot. And then I can also do the same thing for R2, just using those two equations and solving for R1 and R2 is going to be equal to R plus M1 mass, total mass, R. Okay, and then I can also easily get R2 dot. Okay, so then what I'm going to do is I'm going to take R1 dot and R2 dot and put it into the Lagrangian that's up above. And then the potential energy will just be a function purely of R, so I don't have to do anything there. So that's nice. So then I can write down the Lagrangian, and Lagrangian is going to be equal to 1/2 mass. Okay, so I have M1, then R dot squared. Okay, and then R dot, and let me bring out the factor of half because there's a half in front of everything. And I'm going to get here R dot plus, there's a plus here. Yeah, sorry, I forgot there's a plus here and there's a minus here. Okay, so then what we're going to get here is we're going to get R dot M1 times R dot plus M2 R1 divided by total mass quantity squared. Okay, and then I'm going to add M2 times R. What I got there is M1, oh, there's a minus sign there. Okay, quantity squared. Then minus U of R. Okay, so nothing fancy there. So you can kind of go through the algebra there, and what you're going to do is you're going to break out the quadratics, and you're going to get common terms. And the nice thing about things actually simplify out, so it's pretty easy to show this. I'm not going to go through the final steps. What I'm going to get is I'm going to get 1/2 big M R dot squared plus 1/2 times, and the terms I get left over is M1, M2 divided by the total mass, and then R dot squared U. Okay, and U is a function of R. Now, this thing here, this quantity here, the quantity I have here, it has units of mass. We call this a reduced mass. Okay, it's a mass that depends on the two masses. So I'm going to define mu as M1, M2 divided by capital M. And so now my new Lagrangian looks like this. U is equal to 1/2 big M big R dot squared plus 1/2 mu little r squared minus potential energy. So the cool thing about this form of the Lagrangian is that I've actually, by going to a center mass frame, I separate the two motions out. I have motion of the center mass and motion about the center mass. The other thing to recognize is, there's a couple things about this, is that this part here
only depends on the relative position. So that's motion about the center of mass. Potential energy only has R, not big R into it. And then this term here is just the center mass. So this is due to the center mass. And this thing, all this stuff here is motion relative to center mass. Okay. Now, the other cool thing is look at the functionality of the Lagrangian. Lagrangian is not a function of R. That means P, or capital P, or the momentum, generalized momentum associated with that, is equal to a constant. And that makes sense because since there's the only force between the two particles is an internal force, or central internal force. There's no external forces acting on it, so the center of mass will move of constant speed. So that shows up in the Lagrangian. Okay. So now what I want to do is I want to find the equations of motion for this particular Lagrangian. And then what I'm going to do is I'm going to focus specifically just on the relative position to get a simpler equation of motion. Okay, so let's do that. Okay, so this is my Lagrangian here, and for big R and little r, so let's get an equations of motion. And we know that it's cyclic in big R, so using the Euler-Lagrange equation, I'm just going to show that big M times R double dot is equal to 0. That means that R dot, the rate of change of the center of mass, is equal to a constant. Okay, so that's nothing new there. And then, however, the R, okay, and so using Lagrange equation, I can show that the equation of motion is going to be mu times R double dot is going to be equal to the derivative. Now notice this is a vector equation here. So when I take my derivative, I'm going to have to use a gradient. So it's going to be the gradient of u of r. But this basically says mass, mu is an effective mass, times the relative acceleration between the two is equal to the minus the gradient of the central force. So those are my equations of motion. So basically we show that the motion of the center of mass is constant velocity, or momentum is conserved. But then we get this equation here, and so this again is a vector equation because r is a vector. So let's look at that equation more specifically in a polar coordinate system. Okay, that's what we're going to do next. Now, let's think about, and again, I'm using the book terminology for this. So what I'm going to do is I'm going to express things in a two-dimensional polar coordinate system where instead of using rho, I'm going to call this distance r, and then this distance I'm going to call phi. So every point in my polar system is going to be r and phi. I'm not using rho, I'm just following what your book does. I rarely use rho, but for some reason your book uses r. And so then a position vector, r, in this case r, which is the same r that's here, is going to be equal to r hat, and the velocity, r dot, is going to be what we had in the r dot r hat plus r phi dot phi hat. Okay, so this is my equation of motion in general, but let's go back to my Lagrangian and get the equations of motion from Lagrangian. Okay, so let's do that real quick. So if we just ignore the capital R dot term, my Lagrangian is going to be equal. So we're just going to look at, again, when we look at my Lagrangian, we're going to look at the motion relative to center of mass. Notice I get an r dot squared. So if I look at just this term here, okay, because the other term is a constant, what I'm going to show is that L is going to be equal to 1/2 instead of mass, it's mu. So it's mu, then r dot squared. But what is r dot squared? That's going to be equal to r squared. Now, again, that's the scalar thing. R squared phi dot squared minus u of r. Okay, so that's my new Lagrangian, or it's not a new Lagrangian, it's a simplified Lagrangian. Okay, now still the problem is two-dimensional, obviously, because I'm moving in a 2D plane. Okay, so let's get the equations of motion from that. However, look, the Lagrangian is cyclic in phi. So that means that p sub phi, which I'm going to define as L, is going to be a constant. So the angle, so that from there, that Lagrangian tells me the angular momentum is constant, and I expected that because space is isotropic. And so that's going to be equal to partial L respect to phi dot, and so that gives me mu r squared phi dot there by taking the derivative. So that's the that is the angular momentum of the system. So my one main equation, so this is one equation of motion, is that L, which is a constant, is equal to mu r squared phi dot. Okay, so that's one equation of motion there. And then the second equation of motion we're going to get from r. If I take partial L respect to r, that's going to give me minus partial u respect to r. Again, u is a function of r, so I have to do that. But then I got an r here as well. And so that's going to give me there 2 mu r phi dot squared. Okay, that gives me that. And then partial L respect to r dot, that's going to give me mu r dot. Okay, and remember the potential energy does not have r dot in it. And then d dt of that is going to give me mu r double dot. So sticking that all into the Euler-Lagrange equation, mu r double dot is equal to mu r squared phi dot squared, okay, minus partial u respect to r. That's my second equation of motion. Now again, we have both r's and phi's in here, but there's a conserved quantity. And so we're going to use this equation here, solve for phi dot squared, put it into this equation, and we're going to get a one-dimensional equation to solve. So let's do that next. Okay, so now what I'm going to do is I have my two equations of motion. I'm going to basically use equation 1, and I'm going to solve for, so phi dot is equal to L mu r squared. I'm going to square that. That's going to be equal to L squared mu squared r to the fourth. Then I'm going to take that expression and put it in equation 2, so then I'm going to get mu r double dot is equal to, so then I get mu r L squared mu squared r to the fourth minus, now here what I'm going to do is, instead of writing as a partial, u is only a function of r, so instead of writing as a partial derivative, I'm going to write it as a complete derivative, because there's no problem with that. And then what I get is I get this, and then I get L squared mu r to the cubed, and yep, that's right, minus du dr. Okay, so we've seen equations like this before. This says mass times acceleration is equal to something that looks like a force, so basically mass times acceleration, something that looks like a force, and we're going to identify this as a centrifugal term minus the rate of change of that. But really what I want to do is I want to write this as an effective force and thus an effective potential. So what I can do at this point is say, Well, I can write this as minus d dr, and then I have u, okay, and then just 1 second. So I'm going to basically factor out the ddr, so I have u of r, and then from this I can have plus, I'm going to put L squared mu, okay, and then I'm going to have 2r squared. Okay, now you can check that. If I take minus ddr of u of r, I get this term here, and then if I take minus ddr of, let's see here, if I take minus, yeah, that's correct. So then I take minus ddr of this thing here, then that's going to be, okay, so what I'm going to do is I want to factor out the ddr. So if I have here mu r double dot is equal to, I'm going to have minus ddr, okay, and then I'm going to have here u, okay, so that makes sense. And then here I'm going to have plus L squared mu 2r squared, okay, and you can check that. If I take minus ddr of u, I get that term there. If I take minus ddr of this, I get minus L squared mu r cubed, but then the minus times a minus gives me a plus, that gives me this thing here. So the reason why I want to do this is then I can say, well, what is this thing here? This whole thing is a u effective, okay? And then minus ddr of u effective is a force effective. So now what I've shown is basically I've said, so my equation of motion simply looks like mu r double dot is equal to minus d u effective dr, okay, where u effective is equal to u plus L squared over 2 mu r squared. That's it. Okay, that's the equation I need to solve. Now, by the way, I've said nothing. I've given no functional form for the force besides it being a central force. So this is a very powerful method. And remember, this is a two-body problem. Usually two-body problems are pretty hard to solve. But here what I've done is by using the center mass frame of reference, I reduced it down to a one-body problem effectively. And I reduced a very complicated, remember in general, two masses will have 6 degrees of freedom. But by constraining the system in such a way, I reduce it down basically to 1 degree of freedom. And in the end, we can solve this equation, but in the end, all we're going to do is figure out what the potential energy is, write an effective force, effective potential, and then sketch the effective potential. And even just by sketching the effective potential, we're going to solve problems just by looking at the graph of the effective potential. Okay, so that's central force problems. This is a very powerful general method. In class, we're going to look at the Kepler problem, where the central force is gravity. Okay, so where the force is equal to big G m1 m2 divided by r squared. Okay, that's gravity. And then we'll just make up other kind of central forces. It could be, for example, it could be a problem where there's a spring force between the two masses. As long as it's any kind of central force, you can use this method to solve. So we'll see you later. Bye-bye.